All right. Hello, everyone. I hope you're staying safe and keeping up with the lectures that have been posted so far. So, in this lecture, I'm trying something slightly different. I'm also trying to do the screen recording as I am writing the lecture on notability. This means that hopefully by the end of this, we will have a YouTube link that I can share with you all on top of the notability and the PDF files that I typically put up. I imagine that this video is going to take some time because compressing a 1.5 hour video and putting it onto YouTube is quite an achievement, as I've been seeing in my other class. All right. I hope you've been looking at the problems we solved last time. So last time we looked at stability analysis, so I just want to make a quick note of that. So last lecture, we looked at stability analysis. And we did this stability analysis for two types of problems: the simple pendulum problem and then we did this for the bead on the hoop problem as well. And of course, the bead on the hoop problem shows slightly more interesting behavior than the simple pendulum. But then hopefully we will see that towards the end of the course, when we go a little into chaos theory. I want to give a very brief foray into chaos theory at the end of the semester. We will see that the simple pendulum will be revisited again, but with some kind of damping and excitation as well. All right. And the aim for today's lecture is actually to solve a set of problems with some non-conservative forces and torques acting on these bodies. Okay, so for today's lecture, so the aim is to solve a few problems with non-conservative forces and torques actually acting on these bodies, with non-conservative forces and torques acting on the bodies that we are looking at. All right, so let's start off with the first problem. The first problem is a disk on a rolling incline. Okay, and this actually has a lot of similarities to one of the problems in your homework, so which is one reason that I'm actually solving this problem. Okay, so we will look at a problem now. Okay, so here is an inclined surface, and let's say the angle of the incline is some angle alpha. Okay, let me draw this as a dotted line, and this angle here, let me draw it in a different color. This angle here is the angle alpha, and then let's say that we have a disk which is rolling down this incline. Okay, here is the disk. Okay, and let's say that this is rolling down the incline. Here is the center of the disk, and let's say the radius of the disk is capital R. Okay, capital R is the radius of the disk, and let's say that this is a solid circular disk. So this is almost like a laminate or a lamina, thin solid circular disk. And let me say that on top of this there is an external torque that is acting on this body. Okay, so let's say that the direction of this external torque is in the clockwise direction, or the clockwise sense. So this is M applied. Okay, so this is an external torque that is acting on the disk. I just want to make a note of that. So this is an external torque applied in the clockwise sense. And we can, this can be a time varying torque, or this can be a constant torque. It doesn't really make a difference to us. Okay, so That's something that we want to mention here. And the other thing is the disk is rolling without slip. Okay, so there is roll without slip. Okay, and the problem is we need to come up with the equation of motion for this disk. Okay, so determine the equation of motion of a thin circular disk rolling down an incline with an external torque which is denoted as M external acting on it. Okay, and I think in my figure I have written this as M applied, so M external is M applied, and I'm just going to call this as M of T. Okay, this is capital M, and the disk has the following parameters. The radius of the disk is capital R. Let's say the mass is little m. Okay, the disk has a mass of little m and radius capital R. Okay, and it's rolling without slip, which means that the friction force here is the static friction force. All right, so let's do this problem step by step. So the solution. Now I want you to go back to one of the problems that we had seen when we looked at holonomic versus non-holonomic constraints. The 2D rolling without slip disk, that is a holonomic constraint, and I do not want to rehash that, and we will just take that for granted. Okay, so 2D disk roll without slip, this is a holonomic constraint. Okay, and this is the only constraint, which means that the system is holonomic. So this implies the system is holonomic, and this implies that one can come up with generalized coordinates to obtain the equation of motion. And so we can use generalized coordinates, which is equal to the number of degrees of freedom, to write the equation of motion for the disk. Okay, and once again we are not going to go into the details of this, but we can see that one of the generalized coordinates that can be used is the angle theta for the rotation. So I'm going to call that as theta here. This is drawn in the following sense. So this is theta of t. Okay, so the angle theta can be treated or used as a generalized coordinate. And we see that this is a single degree of freedom system. So the number of degrees of freedom is equal to the number of configuration coordinates minus the number of constraints. Okay, and this will be in our problem equal to 1, and so we expect one equation of motion. All right, and very quick rundown of what are the constraints that are typically in this problem is that you have the height of the center of mass is at a fixed distance capital R from the inclined surface. So that's one constraint. The other constraint is the rolling without slip. And so if we treat the generalized coordinates as x comma y and then theta, okay, so this is x comma y here. So if we if the configuration coordinates, I'm sorry. So if we use x of t, y of t, which refers to location of the center of mass of the disk, and if we use theta of t, the rotation angle, okay, if these are your configuration coordinates, okay, these are your CCs, and the constraints, there are two constraints. One is the rolling without slip, and the other constraint is that y of t is equal to r, where x of t and y of t are taken along the incline and perpendicular to the incline. So that's something that we want to specify here. Okay, so here is some x of t and y of t perpendicular to the incline. This is my fixed coordinate frame here. Okay, so this is x and then this is y for me. All right, and so once we do that, we come back here and say, okay, these two constraints are all holonomic constraints, which means that the number of degrees of freedom is 3 minus 2, because I have two constraints, which is 1, and we can use theta of t as the generalized coordinate. To obtain or express the equation of motion. Since the system is holonomic. All right, these are all things that we have already seen in the past, I think. If you remember our lectures from before the beginning of spring break and before the entire world went haywire. So I'm just going through some of these details again. All right, and taking some liberties here, let me set up the coordinate frame, and then let us write the potential and the kinetic energies, and then let us write the Lagrangian formulation for this particular problem. Okay, so let me redraw the disk once again. So here is the incline, okay, and then I have our disk, which is sitting here. So what I'm going to be doing here is I'm going to be drawing this 2 times. Okay, this is 1, and then this is the position of the disk as I move in a time t. So let's say that this is the initial position of the disk. Okay, so this is the initial position. Okay, and then let's say that this is the position at some time t. Okay, and we know that these are all rolling without slip and so on. So I look at the center of mass, here. I draw them by a straight line. I join them by a straight line, I'm sorry. So here is a straight line, and I see that okay, if I now set up a datum, my datum is always going to be a horizontal line. Okay, and this might be perhaps based on the initial position. So I'm going to set up a datum in blue. Okay, so this is going to be the following. So this is my datum. Let me ensure that it is horizontal. Okay, so this is my datum. So horizontal datum. All right, and if I have to find out the location of the center of mass, let me call the center of mass as the point G. So this is the point G at some point in time, at the beginning of time. Let's say initial position t is equal to 0. This is the same point G after some time has elapsed. This is the contact point. Okay. Excuse me. This is a different contact point. Of course, the initial contact point has moved, and the disk is rotating, right? And let me say that, okay, if this is the situation, then if I join these two together by the following, if I join the horizontal line and the line joining the centers by a vertical line, this is going to be called as little h now. Okay, the distance from where the disk center of mass was initially to where it is right now, I'm going to call it as a distance x. Okay, and you can see from drawing the angle of the incline, let's say that here is the incline. Let me draw its angle. Okay, let me extend the incline so that I can actually draw its angle better. So here is the incline, and the angle made by the incline with respect to the horizontal, I called it as the angle alpha, and then it is quite evidently seen that this angle here is also going to be alpha, which means that h is going to be x time sine alpha. Okay, so this tells us that the height h, okay, so height h, which is the height of the center of mass of the disk from the horizontal datum at some arbitrary time instant, little t. Okay, this is h, and we can see from geometry that h is equal to x times sine alpha. Okay, and note here that alpha is a constant angle, and this is the incline angle. Okay, why do we need this height h? We need this because we have to find the potential energy of the disk at some point in time t. We need the kinetic energy of the disk as well. I'm not going to spend too much time on calculating the velocity of the center of mass, because this is something that we know from before. Okay, and so we can see that potential energy is going to be capital V for us, and this is going to be minus mgh. This is because the center of mass of the disk is below the datum at that arbitrary point in time. Okay, so which means that potential energy for us, V, is going to be minus m times g times h, which is x times sine alpha. But then we also know that we are rolling without slip, which implies that x is equal to capital R times theta. Okay, and this is an equation that we can typically obtain by making use of the velocity of the center of mass and the velocity of the contact point, etc. We have already looked at this equation some time back when we looked at holonomic constraints, so I'm skipping the details that are involved in this, which implies that now the potential energy is minus mg r theta times sine alpha. Okay, so here is the potential energy. Let me box this up. Okay, and we are pretty much done with the potential energy. All we have to do is find the kinetic energy and then write the Lagrangian formulation. Okay, now let's go to the kinetic energy term. Okay, so kinetic energy, which is capital T. Now kinetic energy is going to be for a rigid body, right? This disk is a rigid body, so kinetic energy for a rigid body, so T for a general rigid body, we have seen this expression. Okay, capital T is half mvg square plus half times the angular velocity vector transpose multiplied by I about the center of mass, and then omega angular velocity vector. And this can be done in any kind of a coordinate frame. I mean, we have seen that we can perform a change of bases from an XYZ coordinate frame to the principal coordinate frame, which is the 1 2 3 coordinate frame. So in our case, if we write the center of the moment of inertia about the center of mass using the principal coordinate frame, which I'm going to draw in a minute. If we go back to our problem, let me draw that again here. Okay, so if this is the incline, and then if we have the disk which is sitting here, okay, and the principal coordinate frame is going to be the following. From the center of mass, I'm going to have the one direction, okay, which is parallel to the incline. So this I'm going to call as the E1 direction. Then I'm going to have the E2 direction. This is perpendicular, and then I'm going to have the E3 direction, which is coming out of the page. Okay, and the radius of the disk is capital R. Okay, right, we know that. And so if I write this is the center of mass G. Okay, so if I write I Cm, which is I about G using the 1 2 3 coordinate frame, we know that this is going to give us a diagonal matrix, which is one of the main reasons why we are making use of the principal coordinate frame, right? So this is going to be I1 0 0 0, I2 0 0 0, and I3. Okay, and this can be evidently seen for the disk that I3 is half m r square, and I1 is equal to I2 axisymmetric, and this is going to be mr square by 4. Okay, which we really don't need actually in this particular problem. And some other variables that are going to be involved is I'm going to have the angular rate as theta. So the angular velocity I'm going to say is theta dot in the clockwise direction as shown. So this is going to be theta dot of t, which means that if I write the angular velocity vector, this is going to be 0 in the E1, 0 in the E1, theta dot in the E3 direction. Okay, which means that if I now write the velocity of the center of mass of the disk, this we know from before, this is going to be in the E1 direction, and this is going to be r theta dot in the E1. Okay, so please see the problems we had looked at. Before spring break. Okay, we had actually derived these expressions there. All right, now if I write the kinetic energy, so that's going to be T is half m vg square, which is going to be r theta dot whole square. Okay, and then I'm going to have plus half times the transpose of the angular velocity vector, so that's going to be 0 0 theta dot. Then I'm going to have I1 0 0 0, I2 0 0 0, I3 multiplied by 0 0 and theta dot. And if I do the simplifications, then T is going to be half m r theta dot whole square, and then half times, after all the matrix multiplication has been done, this is going to be I3 times theta dot square. And a very quick note to look at here, theta dot actually is going to be minus theta dot because it's acting in the negative E3 direction. So the angular velocity vector really is, if I write it in the vector form, 0 E1 0 E2 minus theta dot E3. Okay, and this is the same way of writing that. Okay, so I3 is mr square by 2, which means that if I do the substitution, so T is half m r square theta dot square, and then half times half m r square, theta dot square. So that's 1 by 2 plus 1 by 4. So that's going to be 3 by 4, which means that capital T is 3 by 4 m r square theta dot square. And I'm pretty sure that this is a problem that you might have solved in, if you have taken basic undergraduate dynamics. This is a problem you might have solved using the Newton-Euler equations. This is just a different way of looking at the same result. Okay. Now one thing that we're going to be doing is bringing back the Lagrangian formulation. So back to the Lagrangian formulation. Right. So here is the Lagrangian formulation for us, and for us the generalized coordinate is theta, and this is a holonomic system. So for a holonomic system, our system, which is holonomic with theta of t as the generalized coordinate, okay, the Lagrangian formulation is the following. If we say that L is t minus v, then we have d by dt of dl by d theta dot is going to be dl by d theta plus q non-conservative theta. Okay. And these are the generalized non-conservative forces corresponding to that particular generalized coordinate. Okay, and this is something that we have to look at. So first thing is, for us, what are the external forces and moments, external torque applied is m of t, and we want to see that this is applied in the clockwise sense. Which means that if I write this as a vector, which means that if I write m applied as a vector, this is going to be minus m of t in the E3 direction, right? Because this is the direction that is into the page. E3 is the same as the EZ direction, if you wish. Okay, and that's something to keep in mind. And then we also have the following. Okay, we also have omega of the disk, which is the body on which the applied moment is acting. This is going to be minus theta dot in the E3 direction. Okay. Now, if we have a torque, this is how we compute the non-conservative generalized torques. Okay, so if we have a torque, have an applied external torque, or if we have a drag torque, say, okay, this is how we will include the non-conservative generalized torque. Okay, and then when we do the next problem, I will summarize and give you a much more general equation that takes care of non-conservative forces, non-conservative torques, and so on and so forth. Okay, so for this case, we're going to have Q J non-conservative torque. Okay, let us say that this is the generalized non-conservative torque corresponding to the jth generalized coordinate. Okay, jth generalized coordinate. Let us say that this is the situation. Then we will have the following formula useful for us: QJNC torque is going to be the summation of all the torques acting on the body. Let's say that, going from I is equal to 1 to whatever, okay, and given by M I dotted with d omega I by dqj dot. Okay, this is a very important term here. I'm going to put a box on this. We're going to be seeing this again in the next problem that we will solve. Okay, put a box around here. Now there is no proof given for this in our particular lecture, and I will post the proof for this in the elaborate notes. I still have to upload your elaborate notes from the previous lecture, so pardon me for not doing that quickly enough. I'll do that very soon. Okay. Now the important thing is this: what does the index I represent? So in the above equation, written, okay, I represents the index I represents the total number of applied or non-conservative torques. This could include drag torque as well. Okay. If acting on the problem. Drag torque is nothing but a torque that resists the motion of the or resists the rotation of the body. Okay. Then omega I represents the angular velocity of the body on which the ith applied or non-conservative torque is acting. Non-conservative torque acts. Okay. And we have qj dot is the time derivative of the generalized coordinate in our problem. So for our problem, back to our problem, we have only one externally applied torque. Okay, we have only one applied external torque, which means that only one non-conservative torque, which means that I is equal to 1 for us. Okay, I'll just rewrite that for our problem. And so mi is just m of t in the E3 direction. Okay, and don't forget that there is a dot product here which I have specified, and then omega of I is going to be minus theta dot in the E3 direction, and qj dot for us is going to be the dot product, the time derivative of the generalized coordinate, which is theta dot for us, which implies that qj non-conservative torque is going to be summation I is equal to 1 to as many number of applied torques, m of I dotted with d omega I by dqj dot, this is going to be, for our problem, minus m of t e3. Okay, this is the direction of the torque that is applied for us. Okay, minus m of t e3, and then you take the dot product with so this is going to be d by dt, I'm sorry, d by d theta dot of minus theta dot e3. Okay, which means that if you do the dot product, time derivative of theta dot with respect to theta dot is 1, which means that I'm going to have qj non-conservative torque is going to be minus m of t e3 dotted with minus 1 e3, which is just going to give me m of t. This is what was expected, okay, if you solve this problem using the Newton-Euler method. Okay, now we go back to our problem. So I'm sorry, I kind of skipped the screen there. Okay, so we go back to our problem and then we write the Lagrangian. So the Lagrangian for us is T minus V, and then we bring back the kinetic energy and potential energy from before. Okay, we had the following expression for the kinetic energy. I'll just scoot that person. Okay, I'm just going to copy that and paste it here. Okay, so this was our kinetic energy, and then I had potential energy as well written some time back. I had a boxed expression for that. Okay, so copy that and then bring that creature down here. Okay, so this was kinetic and potential energies, which means that for us the Lagrangian L is going to be 3 by 4 m r square theta dot square minus of mgr theta sine alpha, so that's going to be plus mgr theta sine alpha. Please note that alpha is the incline angle and it's a constant. Okay, and if we do dl by d theta dot is going to be equal to 3 by 2 mr square theta dot, dl by d theta is going to be mgr sine alpha, because sine alpha is a constant, it does not undergo any differentiation. And then lastly we are going to have qj non-conservative, so q theta non-conservative, the torque, this is going to be equal to the expression that we had written, summation I mi dotted with d omega I by d theta dot, and this gave us m of t, which means putting everything together, d by dt of dl by d theta dot is equal to dl by d theta plus q theta non-conservative, could be force or torque. Okay, so this could be torque plus, if I have any forces, then it's going to be due to the forces as well. Of course, I don't have any applied forces in this problem, so that term is gone, and I just want to make a quick note and say that we did not have any applied non-conservative forces in our problem. Not have any non-conservative forces in our problem. It was rolling without slip, and so the force of friction is the static friction force. That's a constraint force, so it does not enter into the picture here, which means that if I do the crunching, this is going to be d by dt of 3 by 2 mr square theta dot is going to be dl by d theta, which gave us mgr sine alpha, and then that's going to be plus m of t, which means that the equation of motion is going to be the following. D by dt of theta dot is theta double dot. I can get rid of some of these r terms and m terms here, so I'm going to cancel off the mass m. Okay, so I'm going to cancel off the mass m, cancel off the mass m, and then I can divide that by little m here, and then I can get rid of one of the r's in there. I can cancel off this guy here, so if I cancel off r, this is going to be divided by r, and then there is going to be mr squared there, which implies that my equation of motion is going to be the following: theta double dot, and if I divide through by 2 by 3, multiply it through by 2 by 3, then this is going to be theta double dot is equal to 2g sine alpha by 3r, right? The factor of 2 gets cross multiplied, plus I'm going to have 2 by 3 mr square times m of t. Okay, and 2 by 3 mr square is a constant, and in this case sine alpha is also a constant, which essentially tells us that so in our problem m of t need not be a constant, of course, which means that alpha is a constant, so is a constant, and if m of t resulted in a constant, torque applied, then theta double dot would end up being a constant. Okay, and I'll just put a box around this because this is our equation of motion here. Okay, this entire thing. And the nice thing about this problem is this is the first time that we are actually encountering these types of forces where we have generalized forces and so on. So we will be, of course, taking a much slower look at some of these problems until we get used to them. Okay, so this is the end of the first problem, and then we will go and solve another problem which is of a slightly different flavor. I might take some liberties and skip a few steps, and then in the next class what I plan to do is I will start off with a nice problem, and then we will look at the idea of Lagrange multipliers, which will essentially enable us to tackle non-holonomic problems as well. Okay, problems with non-holonomic constraints. So the skate problem that you've seen in your homework, we want to come up with the equations of motion for that. So how do we do that? So that's a non-holonomic constraint, and that's coming up by making use of Lagrange multipliers. Okay, so I'm going to go to a different problem now. Okay, so new problem. This is also once again one of those classic controls problems. This is a pendulum on a cart problem, a pendulum and a cart problem. Of course, in this particular problem, we are not going to be looking at an inverted pendulum as such, and we are not going to be looking at the controllability of the inverted pendulum. We will just look at a generic pendulum cart system. So I'll first draw the figure for the problem, and then we will look at several forces and other things acting on this body here. Okay, so here is a cart, and let's say that this cart is sitting on the ground. Okay, this is the ground surface, and there is a certain amount of friction, let's say, that is involved. Let me give the cart a different color here. Okay, let's make this blue color everywhere. Okay, and here is the cart. Okay, and then at the center of this cart is a pendulum as well, and I need to take this guy here and then bring that down so that I get the entire cart. And then at the center I have a pendulum that is attached. Okay, so by means of a pin system here, I take a pendulum and I bring that creature down here. Okay, so here is a pendulum and a cart. Now the cart is there is a wall here. Let's say that this is the vertical wall, and the cart is attached to the vertical wall at the center of this cart. Okay, by means of a damping element. Okay, so I'm sure you have encountered damping elements in your system dynamics courses. Let's say that there is also a spring here. Okay, and there are other things going on in this problem as well. The first thing is I'm going to have a kinetic friction that is added into this problem. So there is kinetic friction between the cart and the ground. Okay, this is the cart, of course, and suffix C, and then there is the pendulum system. Let's call this point here as the point P, and of course here is the center of mass of the pendulum. So this is going to be G. The length of the pendulum is capital L, little l. Total length is L. So distance from here to there is L by 2 and L by 2. Let me say, let me push these creatures a little down here, and let me say that there is a force that is acting on the cart. Okay, there is a force that is acting on the cart in this particular direction. This is going to be called as F1 of t. Okay, then I'm going to say that there is another force that is acting on the pendulum in the vertical direction at the base of the pendulum. Okay, this is going to be called as a force F2 of t. The damping coefficient or damping constant is going to be little c. The stiffness of the spring is going to be k. Okay, and here is where the force is acting on the body of the cart. And kinetic friction between cart and the ground is going to be given as mu suffix k. Okay, and so here is the problem. Okay, so in this problem we have a cart, we have a pendulum pinned to cart. Okay, and then the cart slides on the ground, on a rough ground, with kinetic friction coefficient mu k. Friction coefficient mu suffix k. Okay, then let's also say that there is a torque which is acting on the body of the pendulum. Let me call this torque as M applied. Let me bring out a different color. Actually, it doesn't seem very evident here. So let's say that there is M applied, M of t. This is an applied torque on the pendulum. Okay, and what is the main aim in this problem is to come up with the equations of motion for the system. Okay, and let me also write that there is a damping element of damping constant C attached to the cart. Okay, then there is a spring element attached to the cart, and the stiffness is K. Let's say mass of the cart is M suffix C. And mass of the pendulum, okay, is M suffix P. Okay, and obviously the idea is we need to come up with the equations of motion. Okay, so the problem is obtain equations of motion. And I say equations of motion because you automatically see that this is a multi-particle or a multi-body system. There are two bodies. There is a cart and there is a pendulum, which means that we are going to be getting two equations typically here. and it's a 2 degree of freedom total system. Okay, so we have the cart here, we have the stiffness K here, the spring of stiffness K, damping constant C, we have the pendulum, several things going on. There is a force F1 of T acting on the cart, force F2 of T acting on the pendulum. These forces remain in the same direction as shown. Okay, that's something that I want to write out as well. So the forces, there is a force F1 of T which is acting on the cart and in the horizontal direction, and then there is another force F2 of T which is acting on the pendulum in the vertical direction. Okay, and the important thing is these forces, these two forces remain in the directions drawn on the problem at all instances in time. At all instances in time. Okay, and our aim is to obtain the equation of motion for the system. Alright, so fairly a formidable problem. We have several things going on in this problem, but we will look at this piece by piece. First thing is we need to look at kinetic energy, and then we look at potential energy, and then we will look at all the different types of generalized non-conservative forces and torques which are acting on this body. Okay, thing that you want to see is there is an applied torque acting on the pendulum only. Okay, alright, so first step is we will obtain kinetic energy and potential energy, then we will look at the non-conservative forces. So our strategy, okay, obtain the kinetic energy and the potential energy of the system. Okay, and which means that kinetic energy of the system, which is T, is T of the cart plus T of the pendulum. Okay, likewise potential energy of the system, which is capital V, is V of the cart plus V of the pendulum. Okay, and we are going to be using the subscripts little c and little p, so which essentially means that capital T is going to be T of the cart plus T of the pendulum, and V is going to be V of the cart plus V of the pendulum, and then the Lagrangian is going to be T minus V. This is the Lagrangian of the system. Okay, and that's our first step here. Okay, this is potential energy. I just want to make sure that's written that way, and once we are done with this, then we will look at the generalized forces, non-conservative forces, and so on. Okay, let's look at the kinetic and potential energies first. So I'm going to redraw the cart. I think I want to just draw the cart and the pendulum only. Okay, so draw cart plus pendulum only. Okay, I'm ignoring all these forces acting because they don't play a role in my kinetic energy. Okay, and so if that is the situation, then I have the following. So here is the cart. Okay, and I'm just going to duplicate that. Sorry, still getting used to these new ideas of teaching. An old dog trying to learn new tricks, or slightly youngish old dog trying to learn new tricks. So bear with me, please. So here is the pendulum. Okay, so the first thing is I look at the center of mass of the pendulum. We call that as the point G. Okay, this was the point P, and then I come up with the variables that define the problem. In this problem, all the constraints are holonomic because there is not much of a constraint from that perspective. The length of the pendulum remains fixed. Everything is in a planar direction, so they're all holonomic constraints. I'm just going to write that out very quickly. So all constraints are holonomic by inspection. Okay, which means that this is a holonomic system. So system is holonomic. All right, and that being said, I'm going to have two generalized coordinates in this problem. One is the point P of the cart. I'm going to say that the cart, of course, can move only in the x direction. So I'm going to have a generalized coordinate x of t that symbolizes the motion of the cart. Then I'm going to have an angle theta that symbolizes the motion of the pendulum, okay, with respect to a fixed vertical line. Okay, so I'm going to draw the vertical line first. So here is my vertical line, and then I'm going to say that, okay, this angle here, this is going to be the angle theta of t, okay, and then I'm going to have the cart, the point P, is going to be described by x of t. Okay, so there are two generalized coordinates in this problem. Okay, so two generalized coordinates, and this is x of t. I'm sorry. And theta of t. Okay, and I can say that the origin of my coordinate frame is set up somewhere in the middle. I can say that, okay, this is the x-axis here, and here is the y-axis, and this is the origin of my coordinate frame. Okay, and here is the point where the pendulum is pinned to the cart. Which means that the velocity of point P is fairly straightforward, and if I say that this is the EX direction and EY and EZ direction, so here is my unit vector system. So this is EX, and then this is EY, this is EX, and then if I say that the direction coming out of the page is EZ, okay, and it can be very easily seen that velocity of point P is going to be x dot in the EX direction. This is only in pure translation, so this is the velocity of the cart, okay, translation only. Okay, then I also have velocity of point G. Now you have to be careful here. Velocity of G is going to be what? For this we can start off by looking at the basic ideas of vector addition, and say that, okay, R G slash O with respect to a fixed observer is going to be R P slash O plus R G slash P. And I'm going to leave this to you to derive the velocity, but I'm going to go to the next step, and then which tells me that velocity of G is going to be velocity of P plus velocity of G slash P. Okay, and I'm going to set up a coordinate frame from the point P all the way to the center of mass, and this coordinate frame is going to be drawn in the following manner. So I'm going to have a coordinate frame which points this way. So this is one direction, and then here is the other direction, and then the third direction, of course, is coming out of the page. So this is going to be E theta, then this is going to be E L. Okay, that is the coordinate frame that I have attached here. And if I were to do this, I would say that this is R P slash O plus, this is going to be L by 2 in the EL direction. Okay, and then you can see that the angular velocity of the frame attached to the pendulum is theta dot, and so if you do the velocity, this is going to be velocity of P is x Ex plus L by 2 d by dt of EL. Okay, and if I complete this, this is going to give me the following. So Vg is going to be Vp plus Vg slash P, which is x dot. I'm sorry, this has to be x dot here. Okay, this is going to be x dot Ex plus, I'm going to have L by 2 and then omega of the frame or the pendulum as such crossed with EL, and I'll skip the details. This is just going to give me L by 2 theta dot in the E theta direction, so which essentially tells me that Vg is x dot Ex plus L by 2 theta dot E theta. Okay, so I have two things now. Let me just put a box around them. One is the velocity of the cart itself. Okay, and the other is the velocity of the center of mass of the pendulum. So that's this creature here. Okay, and the important thing is this: I have to go and do a coordinate transformation from Ex to EL and E theta, which means that coordinate transformation from Ex to EL E theta, and if I look at the coordinate frame, EL E theta and EZ coming out of the page is my coordinate frame. So EL E theta EZ coming out of the page is my coordinate frame, and if I set up the coordinate system, here is what I end up getting. Okay, so here was EL, okay, and this was E theta, and then here was Ex. Okay, I'm sorry, this is not a straight line. So here was Ex, and of course if I look at the angle made here, this angle was theta, which means that this angle is also theta, which means that if I drop perpendiculars from the base of the arrow here all the way down to these two coordinate frames, then I see that this is going to be cosine theta, and that's going to be sine theta. Okay, and so I see that okay, Ex can now be written as cos theta E theta and sine theta EL. And this is the coordinate transformation that we are going to be having to make, which means that Vg is actually going to be the combination of the following. So it's going to be x dot in the EL direction, so that's x dot sine theta EL, and then I'm going to have a combination of x dot cosine theta in the E theta, and then L by 2 theta dot, so that's going to be x dot cosine theta plus L by 2 theta dot in the E theta direction. Let me make sure that the square bracket is placed in the right place. Okay, let me pull this guy out a little bit and then close the brackets here. So this is now the better version of the velocity of the center of mass of the pendulum. Okay, and for the kinetic energy, I'm going to take some shortcuts for this particular problem by saying the following. Okay, so kinetic energy is T of the cart plus T of the pendulum, right? Now T of the cart is easy. This is going to be half m v square p, which is the velocity of the center of the cart. So this is and the mass of the cart, okay, mc. So this is going to be half mc x dot square. And then t of the pendulum, you have to be careful. This is going to be half m pendulum vg square plus, remember that the pendulum is a rigid body and it is in rotational motion. The cart does not have any rotational kinetic energy. I just want to make a note of it. No rotational kinetic energy for the cart, okay. And this is going to be half times omega of the pendulum transpose, I of the center of mass, the moment of inertia matrix, times omega of the pendulum. And making a quick note, I of the center of mass, I can say is the following, okay. If I choose a coordinate frame attached to the center of mass, in this case essentially this is going to be the EL, E theta and the EZ direction. So this is going to be I1 0 0 0, I2 0 0 0, I3 in this problem for me, and I3 is 1/12 MP times L square. Okay, this is a result that we would have seen in probably from undergraduate dynamics, okay. Undergraduate dynamics for a thin slender bar. Okay, all right. So omega of the pendulum, I'm going to snake that term in here. So omega of the pendulum, you can see that the pendulum rotation is in the z direction only. So this is going to be 0 0 and then theta dot. And so if I set everything up together, I get the following. So t of the pendulum is going to be half times m pendulum times velocity of the center of mass square. So this is going to be, you've got to be careful, this is x dot sine theta square plus L by 2 theta dot x dot cos theta square plus, okay, this is going to be half times, if I do if I do the matrix multiplication and then with the column vector and the row vectors, here is what I'll end up getting. This is going to be times I3 times theta dot square, okay. This is what will be obtained, and I just want to make a quick note here and show this is something that you can actually see by doing the multiplication, so I'll skip that particular step, okay. So this is obtained from half omega pendulum transpose ICM omega pendulum term, okay. All right. And so T, which is TC plus TP, is going to be the following. So T is the following, okay. So TC is going to be half m cart x dot square, and then T of the pendulum, if I do the simplification, this is x dot sine square theta, x dot square cos square theta, and so on. So if I add up the like-minded terms, I'm going to have half mp x dot square as well. Then I'm going to have plus a half mp L square by 4 theta dot square term, and then I'm going to have a mixed set of terms, half mp times 2 times x dot cos theta, and I'm going to have an L by 2 times the theta dot term there, and then I'm going to have plus half times theta dot square times 1/12 mp L square, okay. I have some common terms that I can combine together. So T is essentially going to be half m cart plus m pendulum x dot square. So that's one term. There's nothing common to this particular term, the mixed combination of cos theta, theta dot, and so on. So that's going to be the factor of 2 goes on, so that's going to be plus half times mp times L times cos theta x dot theta dot. That's another term there. Then I'm going to have a combination of theta dot square terms. That's L square by 4 and L square by 12. So that's going to give me essentially L square by 3. Okay, if I do the addition, so let me do this pretty quickly. So this is half mp theta dot square times L square by 4 L square by 12. That gives me L square by 3, but then I have a factor of half, so that's an L square by 6 term that I'll end up getting. Okay, so which essentially tells me that the total kinetic energy is half mc plus mp x dot square plus half mp L cos theta x dot theta dot plus 1 by 6 mp L square theta dot square. Okay, so this is the total kinetic energy of the entire system. So that is something that you want to keep in mind. This is not just for one particular body in this problem, this is for the entire system as such. Okay, so this is the kinetic energy of the system. Alright, then we go for the potential energy. The potential energy is fairly straightforward. Okay, so system potential energy. Okay, and for this, if I go back to the cart and pendulum figure from before, I'm just going to copy that figure and bring that down here. Okay, or let me just very quickly draw it out, choose a datum and so on. So if I draw the cart and the pendulum, so here is the cart. And the pendulum, of course, is going to come. So here is the pendulum. Okay, and they are of course pinned together at the point P here. Now I choose a datum that is a horizontal line which is passing through the center point here. Okay, so this is the datum. You got to remember that the cart had a spring attached, which means there is a spring potential energy for the cart. Okay, so V of the cart is going to be V of the cart due to the spring plus V of the cart due to gravity. But there is no gravitational potential energy because my datum is aligned with the center of mass of the cart, so there's nothing much going on in terms of any special effects there. For the pendulum, if I look at the height of the center of mass from the datum, right, if this is what we have here, I'm just going to join them together by a straight line. Okay, this angle here is theta. Okay, and this length is L by 2, which means that this height here is going to be L by 2 times cosine theta. So V of the pendulum is going to be V of the pendulum due to the gravity plus V of pendulum due to springs. Of course, I don't have any springs which are attached on the pendulum, so that term is also going to cancel off, which means that my total potential energy V is going to be V due to the spring, so that's half K times X square. K is the stiffness of the spring, right? And then I'm going to have minus mg L by 2 cos theta, but I got to be careful, this is not just m, this is m of the pendulum. Okay, so this is m suffix p. Alright, so this is the total potential energy of the entire system. Okay, And the last thing that we need to do is look at the generalized forces. So we will quickly go over some of those details now. Okay, so this is the total potential energy of the system. All right, now to look at the generalized forces, okay, generalized non-conservative forces, we now look at the generalized non-conservative forces. We will try to solve as much as possible in this lecture, and then we'll come back and then finish this problem off in the next lecture. Okay, and you're more than welcome to continue looking at this problem as we go forward in the next lecture. Here is a basic idea though for the generalized forces. So let us say that for the jth generalized coordinate, non-conservative forces can be divided into two types. Okay, can be divided into forces that are velocity dependent NCs, okay, and then velocity independent non-conservative forces. Okay, so these are the two types of forces that we typically see. Okay, which means that in general we can say that Qj non-conservative can be broken into, first of all, Qj non-conservative for forces, as we saw in the previous problem, and then Qj non-conservative for torque. Okay, and of course torque can be broken into velocity dependent, non-velocity dependent as well, but we are not really interested in such types of torques. Then we further say that Qj non-conservative is going to be Qj non-conservative forces velocity dependent plus Qj non-conservative forces velocity independent and Qj non-conservative torque. Okay, what are velocity dependent forces, velocity independent forces? Here are the following. Okay, so velocity dependent non-conservative forces these are friction, Coulomb friction, Coulomb friction. Then another type of force that's typically seen in most mechanical systems is a damping force. Okay, these are the velocity dependent non-conservative forces. I just want to put a big box around them. These are the forces that we are typically going to be seeing in our problems. Okay, and let me extend this line here. And velocity dependent independent non-conservative forces, that's the second variety. Velocity independent non-conservative forces, these are typically any externally applied force that is not friction or damping. Okay, this is the second one that we see here. So let me duplicate that and bring that here so that we have another box for this guy as well. Okay, extend that a little bit and complete. I'm sorry, I had a different color given here, so let me just be consistent with that. So this is 1, right? And so how do we write our expression now? Okay, so now let's say that say in our problem, or say in a general problem, let's say, okay, say in a general problem, the index I is the total number of let's say velocity dependent non-conservative forces. Okay, NCs. Okay, I'm just going to say these are velocity dependent forces. Okay, then let's say the index M, let's say index M is the total number of velocity independent non-conservative forces, and then index let's say some I guess I, J, K, L, M, N, O, some index P, Q. I guess I have Q and R used everywhere, so let's say N is the total number of applied torques. Okay, then we have the following. Qj non-conservative is going to be the following. It's going to be Qj non-conservative. As usual, we have velocity dependent forces plus Qj non-conservative velocity independent forces plus Qj non-conservative torques. Okay, and so if I write this out, then watch this carefully. Qj non-conservative is going to be, first of all, summation I is equal to 1 to whatever number f I. I'm just going to say this is velocity dependent dotted with dri by dqj dot plus summation m is equal to 1 to whatever f m velocity independent dotted with drm by dqj, and then lastly the torques. N is equal to 1 to whatever. Okay, this is going to be mn dotted with d omega n by dqj dot. Okay, this is so three things that are going on here. This is to account for velocity dependent forces, and notice the qj dot term. Okay, then this is to account for velocity independent forces, and notice qj without the dot, and then the last term here is of course for the torques, to account for any applied torques. I guess I just have to erase this to account for any applied torques. Okay, and the important thing to see is that the velocity dependent term, you will have the qj dot term in the denominator here for the dot product. The velocity independent force term, you'll see that's only a qj, and then once again when we look at torques, we will look at the angular velocity of the body itself. All right, and so what we will do is we'll come back to this problem, finish this problem in the next class, and then move on to Lagrange multipliers. Okay, so in the next class, next lecture, we will finish this problem. And then look at Lagrange multipliers. Okay, so Lagrange multipliers let me write that out properly. Enable us to look at non-holonomic systems as well. All right, thank you very much for your patience, and I'll see you all in the next lecture. Okay, thank you.